All right, here's the conservation of energy lab that I want you to take a look at. So you have this lab in your lab packet, and you also have access to a blank PDF of this. If you go to Wiley Plus and click on Files and then Lab Materials, it's there as well. So what I'm going to have you do, and you're going to do this on your blank lab that you have, is I'm going to go through this. Okay, so I've already posted the lecture notes for the concepts of conservation of energy. Okay, and the basic concept is for part one is you're going to have a glider. There's your glider. All right, and then someone's going to be holding on to this up here, and we're going to set the potential energy to be zero at the table. So this is your air track. Okay, remember potential energy is always mg times some height above a reference point. So the table is our reference point. Okay, kinetic energy is 1/2 mv squared. Okay, and I think in this portion of the lab I called the mass of the glider capital M. All right, so you have the glider, you have this flag on top of the glider, and you measure the length of the flag. Okay, length is L, and I have that in the data. Okay, so with respect to the table, because nothing goes below the table here, with respect to the table, the glider has potential energy because it has some height, okay, above the table. So the initial potential energy of the glider would be mg times its initial height. Okay, initial kinetic energy is 0 because it's not moving. Okay, so you let go of this here. It accelerates just like the dots lab. Remember the dots, accelerates down the track. And then over here at this final spot, okay, you can measure the final potential energy and the final kinetic energy. Okay, and the final potential energy is mg. Here, I'm going to fix that. I think I'm using capital M's. mg h final. And then for the final kinetic energy, it's moving, so that's 1/2 mv final squared. Okay, so for the initial part, okay, you measure the height from the table up to that little peg on the glider. So that's measured as a number, we know that. Okay, you measure the final height. Okay, we have that, you know that. Okay, now to find the speed, you're going to use the exact same techniques you did for the Newton's second law on an air track. So remember, speed is distance over time. So what the photo gate does, there's a photo gate here, it measures the time it takes this flag to pass through, there's a little photo gate over there, the time for the flag to pass through the photo gate. So the distance that the flag moves is L, the length of the flag, so the photo gate is only on when the flag passes through it. Okay, and then you know the time it takes to go through, and I think I gave you several times and you can measure the average time. So that essentially gives you the speed of the glider at that point. All right, so you know the initial potential energy up here, you know the final potential energy at this final spot, and you know the final kinetic energy. And then you can calculate whether or not energy is conserved. And the way we're going to do that, we're going to calculate what percentage of the energy is lost. So ideally, if it's frictionless, 0% energy should be lost. So here's the same setup. So I wrote down some data. Okay, these are the heights. Remember, with our meter sticks, you measure to 2 decimal places. Okay, I measured the length of the flag. There's my H initial, and I just went through this step by step, and I recorded this data. Okay, and I'm using capital M, 190.72 grams for the mass of the glider. Okay, so for part one, is energy conserved? Okay, so does the energy change? Meaning, is the change in energy 0? So we're going to do that by calculating the percent of energy lost. So this is from the first page. So if I want to calculate how much was lost, I want to know how much changed, divide it by how much I have available. What does that mean? How much do I have available? Okay, well, obviously we're not measuring potential energy from sea level. We're only measuring it from the table. So the energy that it has available from when you let go to when it goes through the photo gate is just the change in potential energy, okay, because it never gets to the floor. I mean, it never gets to the table. So the only available energy you have is the difference in the potential energy from where it starts, which is up here, to the potential energy where it ends, up there. So between these lines, that's the energy available. It's my change in potential energy in absolute value. Okay, because the energy available, that's a positive number, and the change of potential energy is a negative number. Okay. Okay. So my change in energy is final minus initial, and in our notes we have that the total energy, total mechanical energy E, is kinetic plus potential. And I know in the notes I used a U for potential energy because a lot of books use the letter U, but I'll switch back here for PE for potential energy because that's what our book does. Okay, so my final energy minus my initial energy. All right, so that's just my change in energy. So my change in energy is my change in kinetic plus my change in potential, and I'm doing this in absolute value. Okay, because if you wind up with less energy, then that'll be a loss. If you wind up with more energy, which you shouldn't, that would be a gain. So we're just taking this as the absolute value. So as this thing goes down the track, it speeds up. The kinetic energy increases, but it gets lower toward the table, so the potential energy decreases. So kinetic energy increases, potential energy decreases. So this is a positive number. Change in kinetic energy is a positive number. It's going faster. Change in potential energy, that's a negative number because it's going lower. So you're going to find that a positive number plus a negative number should give you around zero, because ideally the energy shouldn't change. You want to know, is the change in energy zero? Okay, and then hopefully it'll be less than 10%. And the track is pretty frictionless, so we should find that the percent energy loss is much less than 10%. Okay. And then eventually when you're done, okay, you can click on this link, and this is the link I have on our module that shows you exactly how and where to submit these labs. They're submitted on our Wiley site. Okay, so I just went through for part one. I let go of this once. I get the time here. I measure the time it takes us to pass through. I bring it back up here. I do it again. Okay, and so I wrote those times right here. I did 2 trials. Okay, and then you're going to record the average. Okay, add those up and divide by 2. All right. So remember, this our timer. The photo gate actually gets the time to 4 decimal places. So your time, average time, is going to be to 4 decimal places. Okay, and then you calculate the final velocity of the glider, or the final speed. You know, the length of the flag, and the T average is that one right there. Okay, so on your lab, you're going to show your calculations. Okay. Part 2 looks like this. Now the track is level. Okay, and let's see. This is going to look like, this looks like your air track, okay? But now, this is horizontal. So someone's going to hold on to this. They're going to let it go from rest, okay? You have a little hanging mass here. That starts at rest. And as this moves to the right, this thing moves toward the floor. So when this thing falls a distance h, okay, let's say h is 80 centimeters. So when this thing goes 80 centimeters down, this thing is going to go, whoops, that thing is going to go 80 centimeters over. Okay, so as much as that one moves down, that one moves over. So when this thing hits the floor, okay, when this thing hits the floor, there's no more tension in the string. So this thing only accelerates from here up to here. So the picture is not to scale, but when this thing hits the floor, the glider's right there. That'd be my height h. That'd be my distance h if the glider moves. So there's a photo gate here. Okay, so the photo gate only turns on when the flag passes through. So that's how you find the speed of this glider, is the final speed there, is the length of the flag, divided by the average time that we'll have data for. So in this case, I'm setting, I'm setting potential energy equals 0 on the floor. Now I'm also going to put a reference point here. Whoops. I'm going to put a reference point here. Okay. And I'm going to say potential energy equals 0 joules at that height for the glider. So the glider is not moving up and down. So I don't need to count its potential energy from the table. I'm choosing another reference point for the glider because its potential energy doesn't change. Okay, so part 2 setup. Okay, I just drew it here. We'll have the data. I have the data for the little hanging mass M. I measured the height. Okay, and I think I'm using capital M, big M for the glider, little m, okay, for the hanging mass, and I have that mass. And so I let go here, and I measured the height that this thing fell, and then I measured the time so that I could find the final speed. Okay, and you want to see whether or not energy is conserved for that case. Okay, so the initial picture, remember, the glider's potential energy doesn't change because it's not going up and it's not going down. So the initial kinetic energy, okay, is I wrote initial kinetic energy for the glider plus initial kinetic energy for the hanger. Okay, so remember, kinetic energy is 1/2 mv squared. So initially, the glider's not moving, little hanging mass isn't moving. So that's why these kinetic energies are 0. Final kinetic energy, okay, for K final, glider's over here, hanging mass is on the floor. So the final kinetic energy, well, I should say the hanging mass is just about to hit the floor. So the final kinetic energy, these things are both moving. Glider's headed that and the hanger's headed downward. The mass hanger's headed downward. So the final kinetic energy is I have the kinetic energy for the glider, and I have the kinetic energy for the hanging mass. And note, they're both moving at the same final speed because they're connected by the same string. Okay. Okay, so here I measured the height, I measured the times, okay, for the glider to pass through the photo gate. Okay, so this time I have there, and that's T4. So you have 2 times. Okay, so your average time is just add up. Your average time, just add these up, divide by 2. That goes there. Okay, so to find the final speed of your glider, the length of the flag divided by that time. And remember, that's the final speed of your glider right here, and that's also the final speed of the hanging mass because they're moving at the same speed. They're attached to the same string. Okay, so for part 1, okay, you're going to calculate, well, here's the data I want you to read right here. Calculate your average time. Calculate your change in height. All this data is in the lab. Okay, calculate that. All right, so for part 1. Okay, so for part 1, so this is the picture for part 1. I just redrew it here. Okay, so your initial, so you want to calculate whether or not energy is conserved. So you calculate initial energy, calculate your final energy. So I'm just doing it piece by piece because remember, energy is kinetic plus potential. Okay, so to find the initial energies and final energies, you look at the picture. So initial kinetic energy, nothing's moving. That's not, or I'm sorry, for part 1, there's only one object. That's the glider. This is initial. That's initial. Well, here, I'll go like this. This is before, and this is after. Okay, so before you let go, or the instant you let go, it's not moving. Okay, so initial kinetic energy is going to be 0. Initial potential energy, here's my reference point, potential energy is 0 joules at the table. So initial potential energy is mg times that initial height. Okay, then you calculate your total energy. The final picture, glider's moving, so you know V final, okay, and you know the final potential energy, which is mg h final, and you have h final. So you'll calculate your final energy. Okay, you'll rewrite your initial energy from up top. And then the lab asks you to calculate your change in kinetic and your change in potential. And just be careful of your plus and minus signs. Okay, just look back up here and make sure whatever numbers you have for initial potential, okay, and final potential, final kinetic, okay, that you watch the plus and minus signs. And then you'll calculate the percent energy loss using your values. And then you'll have a comment down here about your results. Okay. For part two, okay, okay, so this is the picture for part two. All right, so remember this one's sitting here at rest, and then this one's sitting here at rest as well. Okay, and then you let go, and then that one is moving here with speed v final, and then this one's moving here with speed v final. Okay, so here's our data for part two. Okay, so when I calculate my data for part two, or when I calculate what I need to do for part two, right here, like that. Okay. When I look at the initial kinetic energy of the system, well, nothing's moving, okay, because your hand was holding it here. Okay, so V initial was 0. This V initial is 0, so initial kinetic energy should be 0. Okay, initial potential energy, remember potential energy is 0 at the floor, and the potential energy of the glider doesn't change. We talked about that. So the only thing that has initial potential energy is a little hanging mass. Okay, remember potential energy is mg times that initial height. So calculate your E initial. Okay, that's 0, nothing was moving. And then your final picture, when you calculate your K final, okay, that's when you look at the diagram up here and you say, okay, well, the final picture, there's two things moving. You have the glider moving, and you have this little hanging mass moving. So you have two kinetic energies, and I showed that up above. And your final potential energy, the hanging mass is at the floor, so your final potential energy is 0, because the glider's potential energy didn't move. So when you let go, if this is my system, and some books like to make a dotted line and call that the system, the initial energy of the system is all potential. This little hanging mass here has potential energy with respect to the ground. So all the energy is potential. When I let it go, glider's now moving with kinetic, and a little hanging mass has kinetic. So all of the potential energy due to the hanging mass went into kinetic energy for the glider and for the little hanging mass. So you should find that energy is conserved. So you calculate your change in energies, same way you did last time. And again, when you look for K final, okay, you have two things moving. I think I did that up here. Yeah, right? So when you calculate your K final, you have two things moving. You have the glider and you have the hanger. Okay, so try that, and then what I'm going to have you do is as you go through this, you can see the pages that I ask you to submit. Okay, so I have you submit that one, and each page that has the word submit on it, that's what you're going to turn into me.